In this video, we will talk about the relationship between intermolecular force and vapor pressure. So vaporization is nothing but the phase change from liquid to gas, and the reverse we call condensation, and the phase change from solid to liquid is melting, and the reverse is freezing, and the direct conversion of solid to gas without liquid form we call it as sublimation, and the reverse change is deposition. These phase changes occur when there is energy changes. That means for melting and boiling, we have to supply energy. That is going to be endothermic process. So when you heat ice in this heating curve, when you heat ice, it is changing to liquid water. When you heat liquid water, it is changing to water vapor. And so the reverse is going to be exothermic. That means water vapor changing to liquid water is condensation is going to be exothermic, as well as freezing is going to be exothermic. So the energy change for 1 mole of a liquid is called enthalpy of vaporization or heat of vaporization, and we denote that one as delta H vaporization. Likewise, the energy change for melting is called enthalpy of fusion or heat of fusion, and we denote that one delta H fusion. These values are constant for specific substance. So for this heating curve of water, this is for water. So we can see that heat of fusion for 1 gram is 334 joules per gram. And if it is for 1 mole, 6.01 kilojoules per mole. And the heat of vaporization or enthalpy of vaporization per gram of water is going to be 2260 joules per gram, and per mole it is going to be 40.7 kilojoules per mole. So the values are different for different substances, and we have to use the different formula depends on the values given. So if it is in grams given, we can use Q equal M delta H. This is the mass. And if it is in moles, we have to use Q equal N, that is moles, times delta H. So that is here when there is no change in temperature. So for boiling and melting, there is no change in temperature. When there is change in temperature, so when you heat water, so warming of liquid, we use the formula Q equal mc delta T. So mass times specific heat times change in temperature. The specific heat of ice, these values, and for liquid water, we have to use these values. That also depends on whether it is for gram or per mole. Now let us see the reason for no change in temperature at the melting and boiling segments here. So the reason for that one is the energy supplied, the heat supplied is used to weaken the intermolecular forces. What is the intermolecular force you can find in water molecule? That is the hydrogen bonding, right? So the hydrogen bonding between the molecule will get weakened in the solid to liquid, and from the liquid to gas phase, what will happen is it will break that hydrogen bonding. So you can see that on the surface molecule will break that hydrogen bonding when you heat it. So that heat energy is used to break that hydrogen bonding to become water vapor. So that's why the temperature is not increasing at the boiling and melting segments. So in the melting segments, it's just get weakened, and whereas here it is breaking the hydrogen bond. So it requires more heat energy to break it. That is why the segment is longer at the boiling and shorter at the melting, because here we just get it, the hydrogen bond is getting weakened. So in the gaseous phase, there is no hydrogen bond between them. It is free to move around. So this causes the vapor pressure. We can measure that pressure using a pressure gauge. Thus, the vapor pressure is affected by two factors. First one is the intermolecular force of attraction, that is the attraction between the particles, And the second factor is the temperature. So when the intermolecular force of attraction between the particles is less, it is easy to break that attraction. If it is weak, it is easy to break. So if the intermolecular force of attraction is less, it is easy to break the attraction between them. So what will happen is more particles will go to the gaseous phase. So when more particles are going to the gaseous phase, we can say that the vapor pressure will goes up. The pressure created will be high, so the vapor pressure goes up. And what happens when you heat the container? If you heat the container, the kinetic energy of that particle goes up when the temperature goes up, correct? So what happens? It's easy to escape from liquid to gaseous phase. So the vapor pressure will goes up. You can see that this is directly proportional. When temperature increases, the vapor pressure increases. Whereas when the IMF decreases, the vapor pressure increases. So that is inverse proportion, indirect or inverse proportion, and this is direct proportion. All right. So if a substance that vaporizes easily, we said that is volatile. And if a substance that is not going to vaporize easily, we call that one as non-volatile. So volatile substances have more gas phase on top of the liquid, and non-volatile will have less vapor on top of the liquid. Now, if the container is closed, what happens? First, when the container is closed, what happens is the particles here will escape from liquid to gas phase, and after a while, because it cannot escape to the atmosphere, after a while what happens is the particle in the gaseous phase will come back. That means it will condense back. Okay, so maybe more is escaping from liquid to gas and some will condense back to the liquid phase. And at certain stage, what happens is when there is enough vapor on the top of the liquid, what happens is the particles escaping from the liquid is going to be same as particle condensing back into the liquid. So that means whatever is going up is equal to whatever is going down. That means it will reach to an equilibrium position. So that is called dynamic equilibrium. So in that case, how much is the pressure at that particular temperature? We call that is going to be a constant. So say for example, vapor pressure of water at 25 degrees Celsius is going to be constant. So that's because of this establishment of dynamic equilibrium. So by definition, vapor pressure is the pressure exerted by a vapor that is in dynamic equilibrium with its liquid in a closed system. When the temperature changes from 25 degrees Celsius to a different temperature, the vapor pressure of water is going to change as well. So at 25 degrees Celsius, it's going to be 23.8 torr. And if it is going up at 27, for example, it's going to be 26.7 torr. Now let us try to apply this concept in a question like this. Rank these substances in order from lowest vapor pressure to highest vapor pressure at room temperature. So what we have to do is, in this case, they did not talk about any change in temperature. So we have to think about the IMF. So what I will do, I will check each substances given. The first one is acetone, and I will analyze what type of IMF is taking place in this one. I know acetone has a electronegative element here, and there is difference in electronegativity between these two elements that is connected here. So I know this will have a slight negative charge, slight positive charge. That means this molecule is going to be polar molecule. So I will have dipole-dipole interaction in this case. And now I will check the second one. Again, here I can see oxygen. Electronegativity is higher than carbon and hydrogen, right? So what happens is this oxygen will be slightly negative, and also I know that it is connected to hydrogen here. So there is a possibility of forming hydrogen bond here because it is hydrogen with the phone element. So hydrogen with the oxygen. So I can have hydrogen bonding in this case. In 2-propanol, I will have hydrogen bonding, which is stronger than dipole-dipole. And the last one here, methyl propane, I don't see element with a huge electronegativity difference. So I would take it as a non-polar molecule. So in the non-polar molecule, I will have only LDF or dispersion forces. So which one is stronger bond here is stronger IMF is this one, and then second one is this one, and then third one is here. So this one IMF is weaker. That means we will have high vapor pressure here. And then second one is second vapor pressure goes here, and the third vapor pressure is here. So lowest for this one and highest for this one, and in between this one. So lowest vapor pressure to highest is going to be then 2-propanol, and then acetone, and the highest vapor pressure is going to be methyl propane. That's how we can decide the substances with the highest and lowest vapor pressure. Let's try another example. Rank these substances in order from lowest vapor pressure to highest vapor pressure at room temperature. Here also we don't have any change in temperature, all are at room temperature, so I have to analyze the IMF in each molecule. So butane, I can see only carbon and hydrogen, so no big difference in electronegativity, so this is going to be non-polar. So non-polar means I will have only LDF, weak IMF. So weak IMF means it's easy to break the attraction, and so the vapor pressure is going to be high. And then in propanol, I can see a polar bond here. So it will have dipole-dipole interaction, which is stronger than dispersion. So it's going to be stronger IMF compared to butane. So it will have less vapor pressure compared to butane. And now what about acetic acid? I can have hydrogen bond here. So when there is hydrogen bonding, it's going to be stronger. And I can have the polar part here as well. So this is going to be stronger IMF among these three molecules, right? Stronger IMF. So that means stronger IMF means it is hard to break the attraction between the molecules. So we will have vapor pressure least here, least vapor pressure here. And lowest vapor pressure this one, so acetic acid. So we have to arrange from lowest vapor pressure to highest vapor pressure. So lowest is one here, and then this one, and highest vapor pressure is third one. All right, so we can arrange them based on IMF.